Hello everyone, I hope you're all safe and sound. Welcome to the 11th lecture on analog and digital electronic circuits, in which we will study MOSFETs as amplifiers. So I'll begin by introducing the MOSFET. Um, we will study its physical structure and its operation. We will also derive the current voltage characteristics of the device. Then we will use MOSFET to construct a voltage amplifier. So these diagrams, they show the circuit symbols used for the MOSFET. MOSFET is an abbreviation for metal oxide semiconductor field effect transistor. So these transistors, they come in two types. An N-type MOSFET is also called an NMOS, is represented by the two circuit symbols shown in the figure A, whereas the P-type MOSFET, which is also called PMOS, is represented in circuits using these symbols shown in figure B. So as you can see, MOSFET is a four-terminal device. The four terminals include gate, drain, source, and body, denoted by G, D, S, and B respectively. The body terminal may or may not be connected to the source terminal. If it is connected to the source terminal, which is most often the case, then this is the symbol we use, the symbol on the left for the NMOS, and this is the symbol we use for the PMOS, in which the body is connected to the source. If there is no such physical connection between the body and the source terminals, then we use the symbols given on the right. So for an NMOS, the arrow for the body terminal points inwards, and for the PMOS, the arrow for the body terminal, it points outwards. So that is the distinction between the two circuit symbols. So I will discuss the device structure and its physical operation for an NMOS device only. And the corresponding analysis can be carried out for a PMOS device by reversing the polarities of the voltage, node voltages, and reversing the direction of the current. So this figure here shows the cross-sectional view of an NMOS transistor. So an NMOS transistor has N-type uh, drain and source regions, which are built in a P-type substrate, which is also called the body of the transistor. The gate terminal, which is shown here by this electrode. So all of these shaded areas, they represent metal contacts or metal electrodes. So this is the electrode for the source terminal. This one is for the drain terminal. This is for the body terminal, and this here is for the gate terminal. So the gate electrode is connected with the body through this layer of silicon dioxide. So this silicon dioxide acts as an electrical insulator between the gate and the substrate. When there is no gate voltage applied with respect to the source terminal, so first of all of the voltages in the analysis that is going to follow will be measured with respect to the source terminal. So the source terminal will be at the common ground for the circuit. So when there is no voltage between the gate and source terminal, then you can think of the region between the drain and source as a connection of two back-to-back diodes. One of the diodes is formed by the P-N junction between the drain region and the substrate, and the other one is formed by the P-N junction uh, between the source region and the substrate. So this connection of series connection of two back-to-back diodes prevents the conduction of any current between the drain and source, even if there is some voltage at the drain with respect to the source. So when VGS is 0, which is the voltage at the gate with respect to the source, there is no conduction through the transistor. There is no current conducted by the transistor. However, when we apply a small gate voltage with respect to the source, as is shown in this diagram, denoted by VGS. So VGS is the voltage between gate and source. So for small VGS, um, the positive gate voltage, it will, because the substrate is abundant in free holes, the gate voltage, the positive gate voltage will repel those free holes from this region under the oxide away from this region. So the holes will be repelled downwards and away from this region, which will leave behind negatively charged ions. So these negatively charged ions will constitute a depletion region in this area under the oxide layer. This depletion region is shown here by this dotted curve line, this diagram. So as the voltage at the gate is increased and made more positive, more free holes are repelled away from this region, which helps in uncovering more negative charge in the form of negative ions, which increases the depth of the depletion region. Further increase in VGS will start attracting electrons from the electron-rich source and drain regions, because these are N-type semiconductor materials. They are rich in free electrons. So if VGS is increased further, then it will start the positive voltage at the gate, relatively stronger positive voltage at the gate will start attracting the free electrons from the source and drain region into the area under the substrate. When sufficient number of free electrons have been accumulated in this area, then this region between the drain and source, this region of the substrate, which was initially of p-type, because of the abundance of electrons in this region, it turns into an n-type channel. So such a channel is called an induced channel because it is induced by positive voltage at the gate. So this induced channel has been shown by this dotted straight line in this diagram, right under the silicon dioxide layer. So this channel is now essentially an n-type region, which is abundant in free electrons. The gate voltage, which is required to build this conductive channel, or the voltage at which a conductive n-type channel is induced right under the silicon dioxide layer, that voltage is called, that gate to source voltage value is called the threshold voltage, represented here by V subscript PH. So as VGS exceeds V threshold, sufficient number of electrons are accumulated in this region to convert this region into a conductive n-type channel. This threshold voltage obviously is positive for an NMOS device and is a process dependent parameter whose value is typically in the range of 0.3 to 1 volts. Because the gate terminal is insulated from the substrate through this layer of silicon dioxide, it does not draw any current and will take the gate current for the MOS devices to be zero. Please note that since this channel is formed by inverting this region under the silicon dioxide layer from p-type to n-type, the induced channel is also sometimes referred to as the inversion layer. So this positive gate electrode and this negative induced channel, or the negative inversion layer, they can be viewed as a parallel plate capacitor, in which the gate electrode acts as the positive plate This induced channel acts as the negative plate, and this layer of silicon dioxide, it acts as the dielectric between two plates. The positive charge is accumulated at the gate electrode because of the positive gate voltage, and the free electrons in the induced channel, they provide the negative charge. So because of this positive charge on the upper plate and negative charge in the channel, uh, an electric field in the vertical direction from the gate towards the channel is produced. And this electric field actually controls the amount of charge and hence the conductivity of the channel, which is why these devices are called field effect transistors. So when the drain to source voltage is zero, when the drain and source they are at the same potential, then there is no current in this conductive channel. And the voltage between any point in the channel with respect to the source is zero. So the position of a point within the channel is given on this mathematical axis by x. So when x is equal to 0, we are at the source. We are referring to the source region, the boundary of the source region, or the end of the channel at the source region. And when x is equal to L, then we are referring to the end of the channel at the drain region. And we're assuming that the length of the channel is given by capital L. So when there is no voltage between drain and source, VDS is 0. There is no current through the channel, and the voltage at every point in the channel with respect to source is 0. So like I said, we denote the position of any point in the channel with x with respect to the source. So the voltage at that point x with respect to the source, which is given by V subscript xs, is equivalently written as V of x. And this voltage is 0, which means that the voltage between gate and any point in the channel represented by x is equal to VGS. So the voltage between gate and x given by V subscript Gx is actually equal to the voltage at the gate with respect to the source minus the voltage at x with respect to the source. So it is VGS minus Vx. Since Vx is 0, the voltage between gate and any point in the channel is equal to VGS. So the voltage between gate electrode and any point in the channel is the same throughout the channel, equal to VGS. Because of that, the vertical electric field is uniform in strength along the channel from this end to this end, which results in uniform depth of the resulting channel. So the channel here has been shown with a straight line and a uniform depth because the voltage at the gate and any point in the channel is the same. So this results in a uniform depth induced channel, as is shown in the diagram here. And because the channel is induced when voltage at the gate with respect to the source exceeds the threshold voltage of the device, the excess voltage, which is equal to VGS minus V threshold, is called the overdrive voltage, denoted by V subscript OV. And this overdrive voltage, as we will see later on, is an important parameter of the device. Since there is no channel for gate to source voltage value less than threshold voltage, the voltage across this parallel plate capacitor, which is formed by the gate electrode and the induced channel, this voltage, which enables the capacitor to build up the charge, is actually equal to the overdrive voltage. So the voltage that allows this parallel plate capacitor made up of the gate electrode and the channel to store charge is not VGS, rather it is given by VGS minus V threshold, because the channel is not formed unless the voltage VGS exceeds V threshold. So only when VGS exceeds V threshold will we have a channel and a capacitor. So the voltage across the capacitor, which allows the capacitor to store the charge, is then VGS minus V threshold, or the overdrive voltage. This overdrive voltage multiplied by the total capacitance between gate and the channel, represented here by C, gives us the magnitude of the charge stored in the capacitor. In other words, it is the magnitude of the charge stored in the form of free electrons in this channel. This capacitance C is in turn given by the product of the surface area of the channel. So W is the width of the channel and L is the length of the channel. So W times L is the surface area of the channel times Cox. So Cox is called the oxide or the gate capacitance per unit area. So Cox times the surface area of the channel, or in other words, Cox times the surface area of the negative plate, gives us the capacitance of the parallel plate capacitor. So C is given by Cox times WL. Cox in turn, since it is the capacitance of the parallel plate capacitor per unit area, it is given by the ratio of the dielectric constant and the distance between the plates. So from the study of parallel plate capacitor, we know that the capacitance is given by the surface area of the plates times the dielectric constant divided by the distance between the plates. So the capacitance per unit area is then the dielectric constant divided by the distance between the plates. Distance between these two plates equals the thickness of this oxide layer, which is denoted by Tox. So Cox is then given by Eox or epsilon ox divided by Tox, where this epsilon ox is actually the dielectric constant of or the permittivity of silicon dioxide, which is equal to 3.9 times the permittivity of vacuum. So now then, on top of VGS, once we have a channel for VGS greater than V threshold, on top of that, if we also apply a voltage at the drain with respect to the source, so we have a conductive channel. If we apply voltage at the drain, positive voltage at the drain with respect to the source, then this voltage will produce an electric field along the channel from the drain towards the source, which will cause the electrons in the channel to drift in the direction opposite to that of the electric field. That is, it will cause the electrons, it will make the electrons drift from the source end of the channel towards the drain end of the channel. So electrons will be drifted from the source towards the drain through this channel. And this is what gives these regions their names. So the electrons are provided by the source into the channel as they drift through the channel and they end up in the drain. So drain actually collects the electrons drifting through the channel. Hence, this region is called the source region and this is called the drain region. So this flow of electrons from source towards the drain through this channel results in a conventional current which flows from the drain towards the source through this induced channel. And this current is called the drain current and is denoted by I subscript D. So for a fixed VGS, which is greater than V threshold, because VGS has to be greater than V threshold, otherwise there will be no channel available for conduction. So for fixed gate to source voltage, which is greater than this threshold voltage, if we increase the drain to source voltage, then the strength of the electric field along the channel will increase, which will increase the drift of the electrons, which in turn will increase the drain current. On the other hand, if we keep VDS constant and if we increase VGS beyond V threshold further, then this gate to source voltage, this increased gate to source voltage will increase the vertical electric field between the gate and the channel, pointed downwards from the gate towards the channel. And this increased strength of the electric field will attract more electrons from the electron-rich source and drain regions, which will increase the density of electrons in the conducting channel, which in turn will increase the drain current. So we have two phenomena here. Increasing VGS at a fixed VDS will increase the drain current because the electron density in the conductive channel will increase, and keeping VGS constant and increasing VDS will increase the drift of the electrons, which in turn will increase the drain current. So previously, when there was no drain to source voltage, we assumed that the voltage at any point in the channel with respect to the source was zero. But now that we have voltage at the drain with respect to the source, so the voltage at this end with respect to this end is VDS, and voltage at this end with respect to source is zero because this is the same end as the source. So we can readily see that the voltage at any point in the channel is no longer zero. The voltage at the source is zero, the voltage at the drain is VDS, and the voltage at any point in the channel is some value which is non-zero. So we see that as we move from the source towards the drain, then the voltage along the points of the channel, it increases from voltage at the points along the channel, it increases from zero towards VDS, which means that the voltage at the gate with respect to the points in the channel is no longer a constant VGS. Voltage at the gate with respect to the source is VGS, which can be written in terms of the threshold and overdrive voltage like this. So at x is equal to 0 when we are at the source end of the channel, the voltage between gate and source is equal to VGS. And at x is equal to L when we are at the drain end of the channel, the voltage between G and X at x is equal to L is essentially the voltage between gate and drain, which is equal to VGD, which can be expressed as the voltage between gate and source minus the voltage between drain and source. Voltage between gate and source is the threshold voltage plus the overdrive voltage. So the voltage between gate and drain is now given by the threshold voltage plus the overdrive voltage minus VDS. So the voltage at any point along the channel X, it increases from 0 at x is equal to 0 to VDS at x is equal to L, resulting in VGX at x is equal to 0 equal to VGS, and VGX at x is equal to L equal to VGD. And we see that increasing VDS will decrease VGD. So the vertical electric field, because of the voltage between gate and points along the channel, it is no longer uniform. VGS, or the voltage between the gate and a point in the channel, is maximum when x is equal to 0 and is given by VGS. And the voltage between the gate and the point x in the channel when x is equal to L is minimum when x is equal to L and is equal to VGD. So the voltage between the gate and the point x in the channel, it increases from VGS at x is equal to 0 to, it decreases from VGS at x is equal to 0 to VGD at x is equal to L. And hence the strength of the vertical electric field pointing downwards, it decreases progressively as we move towards from the source region towards the drain region. As a result, the induced channel does not have a uniform depth any longer because the strength of the electric field is greater here. So the depth of the channel will be greater here. Since the strength of the electric field is smaller here, the depth of the channel will be smaller here. So this phenomena gives rise to a tapered channel. That is, instead of having a uniform channel, we no longer have a uniform channel. Rather, the shape of the channel is tapered. The depth of the channel, it reduces as we move from the source towards the drain side. As we increase VDS further, the channel becomes more and more tapered. And since the electrons drifting from the source towards the drain region, as they drift from the source, they encounter more resistance in the channel ahead of them because of the smaller depth of the progressively smaller depth of the channel as they move from the source region towards source end of the channel towards the drain end of the channel. So as VDS is increased further, the channel becomes more and more tapered, and the resulting resistance offered by the channel to the drifting electrons, it increases, which, as we will see later on, will decrease the rate of increase of current, ID, with the increasing VDS. So an exact expression for the drain current in terms of voltages VGS and VDS can be found by observing that, unlike before, where we equated the magnitude of the charge with the capacitance, with the product of the capacitance and the overdrive voltage. Now the magnitude of the charge depends on the point in the channel, because uh, the electric field between the gate and the channel, it depends on the point in the channel, because the electric strength of electric field decreases from x is equal to 0 to x is equal to L. So previously, when the voltage between the gate and any point along the channel was fixed VGS minus V threshold, now the voltage between the gate electrode and a point in the channel is not fixed anymore. So it is given by VGS minus V threshold minus Vx. So previously Vx was 0, but now Vx is not 0 anymore. So the voltage between the gate electrode and a point X in the channel is given by VGS minus V threshold, which is the overdrive voltage, minus Vx. This makes the magnitude of the charge within the channel a function of the point in the channel X. So we can find the resulting drain current by computing from this equation the magnitude of the charge per unit length, and then multiplying it with the drift velocity of the electron. So this here is the charge per unit length, which has dimensions of coulomb per meter, and the drift velocity of the electrons is given in meters per second. So their product will have a dimension of coulombs per second, which is equal to the current. So charge per unit length drifting with this velocity, when multiplied with this velocity, gives us the resulting current in the channel. So we know from basic physics that the drift velocity of the electrons is given by the mobility of the electrons. So mu n is the mobility of electrons at the surface of the channel times the electric field along the channel, Ex. Because the voltage at different points along the channel is not fixed anymore, we will have the strength of the electric field along the channel will be a function of the point in the channel at which we are observing the electric field. So this electric field is given by the negative gradient of the resulting of the underlying voltage Vx. So the drift velocity is given then by this relation. So if we put this equation back here, then the drain current is given by this differential equation, which can be integrated over the length of the channel like this. So we take dx onto the other side. So the differential on the left-hand side is dx. So we integrate it over the length of the channel, and differential on the right-hand side is dvx. So we integrate it over the voltage along the length of the channel. So at x is equal to 0, the voltage at x is 0 because we are at the source, and the voltage is measured with respect to the source. So voltage at x when x is 0 is equal to 0, and the voltage at x when x is equal to L is equal to VDS, because at x is equal to L, we're at the drain side of the channel. So the voltage at x when x is equal to L is equal to VDS. So integrating the left hand side over x from 0 to L and the right hand side over Vx from 0 to VDS, we get this equation for the drain current, in which mu n is the mobility of the electrons, Cox is the oxide capacitance per unit area, and W over L is another very important parameter for the MOSFETs. It is called the aspect ratio. We also see that the drain current is a function of the overdrive voltage and the resulting drain to source voltage. So the drain current can be seen to be proportional to mu n and COX, because increasing mu n will yield larger current. Of course, greater the mobility of electrons, larger the value of the current, and the greater the value of COX, uh, greater is the charge density in the channel. So greater the capacitance, greater is the accumulated charge of the parallel plate capacitor. So which in turn will increase the resulting drain current. So increasing either mu n or COX will result in an increase of the drain current ID. So this product of mu n and COX is represented by Kn prime and is called the process transconductance parameter for the MOSFET. And the product of process transconductance parameter with the aspect ratio W over L of the device is called the MOSFET transconductance parameter, and this is denoted by Kn. So in terms of Kn prime and Kn, we can write the drain current like this. And we see that since the electrons that are the flow of electrons that is initiated from the source, it terminates at the drain, or in other words, the flow of positive charge which is initiated at the drain, it ends at the source. The drain current is always equal to the source current, which is denoted by I subscript N. So for a MOSFET, the drain current will be equal to the source current, and its gate current will be equal to 0, will be taken to be 0. So looking at this equation 10 for the drain current, we see that there are two components of the drain current. The first component tends to increase ID with increasing VDS, which makes sense because when VDS is increased, then the electric field along the channel from drain to source, it increases, which increases the drift of the electrons from source to drain, which in turn will increase the conventional current ID. On the other hand, we have this other term, quadratic term, which tends to, because of this negative sign, this tends to decrease the drain current ID. And this actually reflects the idea that I discussed before, that with increasing VDS, the channel becomes more tapered, and the resistance offered by the channel to the drain current increases. So this idea is, or this notion is encapsulated quantitatively in the expression for the drain current by this term. So together, these two terms, they determine the value of the drain current through the conductive channel from drain towards the source. When the drain to source voltage is small enough, so because there are two components, we can assume that this component, because it is a quadratic function of VDS, for small values of VDS, this term will be very small. So when VDS is small enough such that this term is much, much smaller than this term, which is to say that VDS is much, much smaller than twice the value of the overdrive voltage for a fixed VGS, then this term can be ignored. And the resulting drain current can be approximated by this linear expression. So if we look at this expression, then the ratio of VDS to ID is equal to 1 over this term. So since the ratio VDS to ID is the ratio of the voltage between drain, voltage of the drain with respect to the source to the drain current flowing between drain and source, this ratio VDS over ID can be called as the resistance of the channel between drain and source, because it is the ratio of the voltage of the drain with respect to the source to the current flowing from the drain towards the source. So VDS over ID is called RDS, which is the resistance between of the conductive channel between drain and source, and is given by the inverse of this term. By definition, resistance is inverse of conductance. So this GDS is the conductance of the induced channel, and it is given by this expression. So we note that this approximation here in equation 11, this is equivalent to substituting Vx is equal to 0 in equation 3 and Ex by this constant value in equation 5. So if we go back to equation 3, then if we assume Vx to be 0, and if we replace Ex with Vds over L, then we won't have this term, and this will be a constant Vds over L. This term will be gone and will be left with the first term as we do here, as we get here. So this approximation is equivalent to substituting Vx is equivalent to assuming Vx, which is the voltage at a point x in the channel with respect to the source. So this is equivalent to assuming Vx to be 0 and Ex with this constant value Vds over L, which in turn is equivalent to assuming uniform depth for the induced channel, because we know that when Vx is 0, then the voltage between gate and x, which is a point in the channel, is equal to Vgx, which in turn is equal to Vgs because Vx is 0. So that voltage is constant along the channel, which results in constant vertical electric field, which gives us uniform depth of the channel. So this approximation just says that for small enough VDS, the channel is still approximately uniform in depth, and it behaves like a linear resistor, whose value is given by this expression. So if we analyze this expression, then the resistance of the channel, it decreases with increase in mu and in Cox, because increasing mu and in Cox will increase the drain current, as discussed before, which in turn will decrease RDS. Furthermore, increasing the width of the channel will, as expected, reduce the resistance, and increasing the length of the channel will increase the resistance. Apart from this term, the resistance also depends on the gate to source voltage minus V threshold, or in other words, it depends on the overdrive voltage. So this resistance is actually a voltage controlled resistance. Its value is given by VGS minus V threshold. So increasing this overdrive voltage will decrease the resistance, because increasing the overdrive voltage, since overdrive voltage when Vx is 0, we can think of the gate electrode and the uniform depth channel as the parallel plate capacitor, as we discussed before, and the charge accumulated on the negative plate is directly proportional to the overdrive voltage. So increasing the overdrive voltage will increase the magnitude of the charge in the channel, which will increase the current in the channel, and hence it will decrease the resistance of the channel. So as a side note, please note that these devices in which a channel is induced by applying a VGS greater than V threshold, and then it is enhanced, that is the conductivity of the channel is improved by increasing the overdrive voltage. Such devices are called enhancement type MOSFETs. So we conclude that for this enhancement type MOSFET, when VDS is small enough, its drain current and drain to source voltage, they are approximately given by this linear relationship, from which we conclude that we can see that the MOSFET behaves like a voltage controlled resistor. So this operation of the MOSFET, of the in particular this NMOS, is called the operation in the triode mode. So this exact equation here of the drain current is called the triode mode drain current. of the NMOS. And for small enough VDS, MOSFET in the triode mode acts like a voltage controlled resistor. So as the drain to source voltage is increased, gate to drain voltage decreases according to this expression. So when VDS is increased to overdrive voltage, when VDS, in other words, when VDS equals VGS minus V threshold, then the voltage between gate and drain, VGD, drops down to V threshold. And since the voltage between gate and any point along the channel must exceed V threshold for a channel to form at that point in the first place, when VGD drops down to V threshold, then the channel at the drain side ceases to exist. This is called the channel pinch-off phenomena, meaning that when VDS increases to the overdrive voltage value, VGD drops down to the threshold value, and the channel is pinched off at the drain side. However, please note that this does not mean that the drain current is blocked. The electrons drifting from the source side, they still conduct current through the channel, and as they reach the drain side of the channel, they are swept across the depletion region by the electric field in the depletion region around the drain region. So those electrons, they are swept across the depletion region and are collected into the drain. So the drain current continues to flow. However, we note that increasing VDS beyond the overdrive voltage does not have any effect on the shape and hence the charge, on the shape of the channel and hence the charge contained in the channel. So the resulting drain current, it becomes independent of the drain to source voltage, and hence it becomes constant. And its value is given by this expression. So this expression is obtained by replacing VDS in the equation for the drain current in the triode mode. So in that equation, if we replace VDS with VGS minus V threshold, because this phenomena occurs when the channel is pinched off. So channel gets pinched off when VDS equals VGS minus V threshold. So at that point, at that voltage and beyond, the current becomes constant, given by the value of VDS equal to VGS minus V threshold in the triode mode drain current equation. So replacing VDS in that equation that we derive for the triode mode, replacing VDS with VGS minus V threshold, we get this equation for the drain current. So we can see that it is independent of the drain to source voltage. So changing the drain to source voltage does not change the drain current. Hence, it becomes constant with respect to the drain to source voltage. However, it has a quadratic dependence on VGS. So if we treat the gate and source terminal as the input port and drain and source terminals as the output port, then VGS becomes the input voltage and drain current becomes the output current. So in that context, the output current is given by an amplified version of the input voltage. So MOSFET is said to behave like a voltage controlled current source. And this behavior of MOSFET, that is when the drain current becomes constant, then the MOSFET, when it behaves like a voltage controlled current source, is said to be operating in the saturation mode. So this is the equation of the current when the MOSFET is operating in as a voltage controlled current source in the saturation mode. So from the expression of the drain current in the triode mode given in equation 10 and the expression of the drain current in the saturation mode, which is by the way also called the saturation current given in 15, we see that the drain current increases with the drain to source voltage in the triode mode, and it becomes independent of the drain to source voltage in the saturation mode. So these two equations can be used to draw the ADE VDS and ADE VGS characteristics of the device. So in this circuit, we excite the NMOS with the different values of VGS and VDS. So for a given VGS, we vary VDS, and then we we change VGS to a new value and vary VDS again. So doing this, we get a family of curves at different values of VGS, which are called the ADE VDS characteristics. So here at VGS equal to capital VGS1, since capital VGS1 has been assumed to be smaller than the threshold voltage, so at small VGS equal to capital VGS1, there is no conduction through the MOSFET because there is no channel. And hence the MOSFET is said to be in cutoff mode. So this straight line, this horizontal line on the x-axis, it represents zero current as we vary VDS. Hence it represents the operation of the device in cutoff mode. For all the other VGS values, VGS2, VGS3, they are all assumed to be greater than V threshold, and hence at all other VGS values, the device conducts either in the triode mode or in the saturation mode, depending upon the value of VDS. So for example, at capital VGS2, when the device, when the voltage VDS exceeds VGS2 minus V threshold, then the device operates in saturation mode. So that point on the curve is represented by this VOV2. So VOV2 represents the overdrive voltage at VGS2. So VOV2 is actually VGS2 minus V threshold. Similarly, VOV3 is VGS3 minus V threshold. And VOV6 is VGS6 minus V threshold. So these vertical lines, they represent the value of the overdrive voltage at different VGS values. The corresponding saturation current is given by these expressions. So this equation in 15, it can be written in terms of by replacing this product with the MOSFET transconductance. It can be written in terms of Kn. So the saturation current for VGS2 is given by half Kn times VOV2 square, which is VGS2 minus V threshold whole square. And the saturation current at VGS6 is given by half Kn VOV6 square. So VOV6 is VGS6 minus V threshold square. So these, they represent these values, they represent the saturation current for different values of VGS. So for a given VGS, the operation of the device to the right of these vertical lines represents the saturation mode of operation of the device. And the region of the ADE VDS characteristics to the left of these vertical lines, because because for a given VGS, when VDS is smaller than the overdrive voltage, then the transistor operates in the triode mode. So for a given VGS, the region towards the left of these vertical lines represents the triode mode region. So these points, they represent the boundary between the triode and saturation mode. And they can be seen to lie on this parabolic curve. Because from 15, we see that the saturation current has quadratic dependence on VGS. So this results in a parabolic plot of this equation. So ID being quadratically dependent on VGS suggests that these values of the saturation current, they lie on the parabolic curve, which is shown by this dotted curve here. So this dotted parabolic curve actually is actually the plot of this equation, and hence represents the ID VGS characteristics in the saturation mode of operation of the device. So the region of the ID VDS characteristics to the left of this parabolic curve represents the triode mode, and the region of the characteristics towards the right of this parabolic curve represents the saturation mode of operation of the device. A similar analysis can be carried out for a PMOS transistor, the cross section of which is shown in this diagram here. So a PMOS device consists of P-type drain and source regions, which are grown or built in an N-type substrate. So applying a negative gate voltage with respect to the source repels the electrons right under the oxide layer away from this region. And for a suitably large negative value of VGS, the holes in the source and drain region are then attracted and accumulated under this region of the substrate. And this essentially converts this region under the oxide layer into a P-type conducting channel. So that happens when VGS, the magnitude of VGS becomes greater than the magnitude of the threshold voltage for the device. That is, VGS becomes so negative that this portion of the substrate under the oxide layer becomes a P-type conducting channel. And then applying a negative VDS causes source current, a conventional source current, to flow from the source through the channel towards the drain. So by reversing the polarities of all the voltages and by reversing the direction of the current, we can obtain similar relationships that we did for the as we did for the NMOS device. So from the equation of the drain current in the saturation mode, which I'll call the saturation current, given in 15, we see that the drain current is proportional to the square of the gate to source voltage. So the drain current has quadratic dependence on the gate to source voltage. So like I said before, if we treat the gate and source terminals as the input port and drain and source terminals as the output port, then the drain current becomes the output current and VGS becomes the input voltage. So for a given VGS, for a given input voltage, we get an amplified output drain current. So MOSFET can be viewed as a transconductance amplifier when it is operating in the saturation mode because it produces large output current corresponding to a given input voltage. So this transconductance gain of the MOSFET when it is operating in the saturation mode can be converted into the voltage gain by connecting a resistor RD at the drain. So in this circuit, we have connected the NMOS through RD with the source, with the power source VDD. So VDD is the supply voltage. And we treat the gate and source terminals as the input port, which is excited with the voltage VGS. And we treat the drain and source terminals at the output port and measure the voltage VDS and the current ID as the output voltage and output current respectively. So since source is common between the input and output ports, this configuration is called a common source configuration for the NMOS amplifier. So the output voltage VDS, so the amplification we obtain in ID can be mapped to VDS through this circuit. So VDS is given by VDD minus ID times RD. So when the device is operating in saturation mode, ID is given by this quadratic expression. And hence, this expression of VDD minus this quadratic expression times RD gives us the output voltage VDS. So we can see that for a given VGS, the output voltage depends on the square of VGS and hence is amplified in value, in magnitude. So this equation, which represents the operating point of the circuit, is called the load line. And due to the negative sign in this expression, we see that the output voltage VDS is out of phase with respect to the input voltage VGS by 180 degrees, which is why this common source voltage configuration is called an inverting configuration. So here I plot the load line superimposed with the ID VDS characteristics of the NMOS device. So this straight dotted line shown in magenta color is actually the plot of this equation. So when ID is 0, the device is in cutoff mode, and VDS is given by VDD. So this corresponds to this point of the line. And when VDS is 0, then ID is given by VDD over RD. So this corresponds to this end of this straight line. So the operating voltage and current of the NMOS voltage amplifier, it always satisfies this linear equation. That is, the operating point is always found uh, on this straight line. Since NMOS must be operated in the saturation mode to obtain any voltage gain, we must ensure the operation of the NMOS within this region of the characteristics, that is towards the right of this parabolic curve, which means that we must ensure that the operating voltages and currents, they lie within this portion of the load line, which is towards the right of the parabolic curve. So in order to do that, we must apply appropriate DC voltages at the input, and application of appropriate DC voltages to ensure the operation of NMOS in the saturation mode is called the biasing of the NMOS device, as is shown in this circuit here. So this is the same common source amplifier, but in this case, we have decomposed the gate to source voltage into two components. Small VGS is the component of the gate to source voltage, which is to be amplified by the transistor. So this is the signal to be amplified. Whereas this capital VGS, it is the DC biasing voltage. So the sole purpose of this capital VGS is to bias the NMOS transistor such that it operates in the saturation mode. So the bias point, which is the combination of the DC component of the drain current and the DC component of the drain to source voltage. The bias point is the response of the device to this DC voltage VGS. So the bias point, which is the DC value of ID and VDS, is found by killing this small signal source VGS. That is by observing the response of the device to this capital VGS. So since the device is supposed to be operating in the saturation mode, when we set small VGS to 0, the gate to source voltage becomes equal to capital VGS, and its drain current is given by this saturation value, in which we simply replace small VGS with capital VGS, and the resulting DC component of the output drain to source voltage is given by the same expression. The only difference is that now we use the DC component of the drain current, which gives us this relation. So this gives us the bias point of the circuit at the output. Now, since the total gate to source voltage is the sum of these two voltages, the total drain to source voltage at the output is given by VDD minus the total drain current times RD. The total drain current is given by the total gate to source voltage through this quadratic expression. So this relation here in expression 19, which relates the output drain to source voltage with the input gate to source voltage, represents the voltage transfer characteristics of the amplifier, which are shown here in this diagram. So these characteristics are divided into three parts, and each part corresponds to a separate mode of operation of the device. So when VGS is smaller than V threshold, so this vertical line here, it represents the value of the threshold voltage on the x-axis. So when VGS is less than V threshold, the device is in cutoff mode. There is no current flowing through the circuit, and the drain to source voltage equals the supply voltage VDD. So this horizontal straight line refers to the cutoff mode of operation of the device. And as soon as VGS is increased beyond V threshold, the device starts to conduct in the saturation mode. Why in the saturation mode and not in the triode mode? Because prior to conducting, the device already has a large VDS. So as soon as the device starts conducting, its VDS is very large, is large. So this corresponds to, so if we go back to the ID VDS characteristics, then the device turns on when we are in this region of the load line. So this region of the load line corresponds to the saturation mode of operation of the device. So as soon as the device turns on, it starts operating in the saturation mode. the current, which is quadratically related to the gate to source voltage, increases. As the gate to source voltage increases, the corresponding drain to source voltage decreases. Uh, and we get a curve of this shape. So this curve represents the operation of the device in the saturation mode. And this curve refers, so by looking at this curve, we see that there is a large change in the output voltage for a given change in the input voltage VGS. So the slope of this curve, because this curve is nonlinear, the slope of this curve, which must be computed at a given point, refers to the voltage gain of the amplifier. Because the slope of the curve, by definition, is the change in output voltage divided by change in input voltage, which is the voltage gain of the amplifier. So, like I said, this curve is nonlinear, so the slope must be computed at a given point. So I compute the slope at small VGS equal to capital VGS. So the slope is computed by differentiating this equation of VDS with respect to small VGS, and then replacing small VGS with capital VGS. So this gives us this expression for the voltage gain of the amplifier. So this negative sign again indicates the inverting nature of the amplifier. So the gain of the amplifier in the saturation region is given by the MOSFET transconductance, the overdrive voltage corresponding to capital VGS, and the resistance RD. So as VGS increases further, VDS drops down to this value here. So this point here on the curve represents the boundary between the triode mode and the saturation mode. That is, this is the point at which the output drain to source voltage drops down to the overdrive voltage corresponding to VGS. So at this point, if we denote the gate to source voltage by VGS, capital VGS naught, then the drain to source voltage, which is labeled as capital VDS naught, is equal to the overdrive voltage corresponding to capital VGS naught. So as VGS is increased further, the drain voltage, as VGS is increased further, the drain voltage decreases and the device enters the triode mode. So why does VDS fall below capital VDS naught for increase in VGS beyond capital VGS naught? So we can answer this question by going back to the slide in which I showed the load line. So the operating voltages and currents, they always lie on this straight line. So as soon as the transistor enters the triode mode, then the operating voltages and currents, they lie on this portion of the line. They are given by this portion of the line. So in this portion, you can see that increasing VGS will increase the drain current. So for example, at VGS equal to VGS4, the drain current is given by the y coordinate of this intersection between the line and this curve. Similarly, at VGS5, the drain current is given by the y coordinate of this intersection. And at VGS6, the drain current is given by the y coordinate of this intersection. So there is an increase in the drain current, but you can see that there is not much difference between, the increase is really small. The difference between this y coordinate and this y coordinate is very small. And the difference between this y coordinate and this y coordinate is even smaller. So as VGS increases in the triode mode, the drain current will increase, but the increase will be very small. In fact, the increase in current will become progressively smaller as VGS is increased. Hence, the output drain to source voltage will decrease, but the decrease will be very small. And the decrease will eventually, the rate of decrease of the drain to source voltage will eventually reduce. The rate of decrease of drain to source voltage will decrease in itself because with increasing VGS in the triode mode, the rate at which the current increases decreases. So the rate at which the voltage VDS decreases will decrease with increase in VGS. So you can see that the drain to source voltage becomes almost constant. So there is almost no gain in the triode mode, and there is definitely low gain in the cutoff mode. The only change in the output, appreciable change in the output voltage for a change in the input voltage is observed when the device is operated in the saturation mode, and this is the resulting gain. So we can find the coordinates of this point, which marks the boundary between saturation and triode region, by replacing VGS with VGS naught, capital VGS naught, and VDS with capital VDS naught in this equation. So I've replaced small VGS with capital VGS naught and small VDS with capital VDS naught. Capital VDS naught is capital VGS naught minus V threshold. So rearranging the terms, we get this quadratic equation, which can be solved like this. So this is one of the roots of this quadratic equation. The other root gives us, the other solution gives us negative VGS. So the other solution is negative because we have a negative sign here, which would mean that the gate to source voltage is smaller than threshold voltage. But that is not true. The device is conducting. So we discard the other solution because the other solution is erroneous. So using this solution, we can find capital VGS naught as the sum of V threshold in this term, and capital VDS naught is given by, which is equal to this expression is given by this term. So here in this slide, I visually show the amplification obtained from the common source NMOS voltage amplifier. So I excite the amplifier with the source signal, which is sinusoidal at frequency 1000 Hertz, having a peak value of 100 millivolts. And I bias the transistor with the gate to source voltage of 1.2 volts. So this vertical dotted black line, it represents capital VGS of 1.2 volts. And this sinusoidal blue signal riding on top of it is the small VGS. So this capital VGS biases the transistor at an output DC voltage, at an output DC drain to source voltage of 2.67 volts, which is represented by this dotted line here. And the AC component of the output drain to source voltage is represented by this inverted sine wave. So this inverted sine wave plus this 2.67 volts of DC voltage, this represents the total drain to source voltage at the output. So I've used an RD of 12 kilo ohms and I have set the supply voltage to 5 volts. So this refers to 5 volts. So you can see that this 2.67 volts biases the transistor almost in the middle of the saturation mode. So please note that this diagram is up to the scale. So this is drawn to the scale, which means that for an input voltage which is actually this small, riding on top of DC value, we get a large output voltage which is riding on top of this DC value. So this visually shows the amplification obtained from the common source NMOS voltage amplifier. Since the gain of the voltage amplifier in the saturation mode depends on the value of RD, and the output DC value of the drain to source voltage also depends on RD. We see that if we increase the value of RD, then the output DC component of the drain to source voltage, which is given by this expression, it decreases. So increasing RD will decrease VDS, which in turn will shift the Q point down the VTC. So the output DC value of the drain to source voltage will decrease, which will shift the Q point down the voltage transfer characteristic, which in turn will leave smaller room for the tail swing of the output voltage. That is, there won't be enough room left for the output voltage in the negative direction, because as soon as the instantaneous value of the output voltage goes below capital VDS naught, then the device enters the triode mode, and in the triode mode we observe almost uh, zero voltage gain. So this is demonstrated, this effect is manifested by the clipping of the negative peak. So as soon as the device enters the triode mode, the negative peak is clipped off. So here please note that we haven't changed the DC input biasing voltage, and we are using the same VDD. The only difference is that we have increased the value of RD, which has shifted the Q point downwards and have resulted in the cutoff in the clipping of the negative peak of the output voltage. On the other hand, if we decrease the value of RD, then the DC component of the output drain to source voltage, it increases, which in turn shifts the Q point up the voltage transfer characteristic, and hence leaves a small room for the voltage head swing. That is, it leaves a small room for the swing of the output voltage in the positive direction. So this phenomena is depicted here in this figure. So please note that I have kept the input DC biasing voltage VGS and the supply voltage VDD the same. However, in order to demonstrate the clipping of the positive peak, I have increased the peak value of the source VGS to 450 millivolts, keeping the frequency the same. So decreasing RD increases the output DC DC component of the output drain to source voltage to 4.42 volts. So as the output voltage swings in the positive direction, it rides over this DC value, which is given by this dotted horizontal line. So as it rides over this DC value in the positive direction, the output voltage is flipped off at VDD. Because the output drain to source voltage cannot exceed VDD, because if it did, then it would mean that the drain current would flow in the opposite direction, which is not possible. So as soon as the output drain to source voltage approaches VDD, it is clipped off at that point. So decreasing RD shifts the Q point upwards, which results in the clipping of the positive peak. Because as the voltage approaches VDD, the current, the drain current through the device, it reduces, and eventually the transistor goes into the cutoff mode, at which point the positive peak of the output voltage is clipped off. So to conclude, MOSFET must be operated in the saturation mode for its use as an amplifier. Furthermore, the MOS amplifier operating in the saturation mode should be biased such that the output DC voltage is right in the middle of the saturation region of the voltage transfer characteristics, because this will leave maximum room for the swing of the output voltage both in the positive as well as in the negative direction. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.